The next couple of examples are similar. You're still using F equals ma, but it's just getting a little bit more complicated. There's a few more things thrown in there. Anyone still writing? So, when objects are lifted or pulled by strings, springs, ropes, or cables, or just any kind of attachment, the force applied is by the string, spring, rope, or cable is called the tension. Okay. So, for example, a crane lifts a block of metal of mass 200 kilograms upwards at a constant speed of 0.5 meters per second. Calculate the tension in the cable attached to the top of the block. So when we've been talking about rockets and things, we've been talking about the thrust of the engine. In this case, we're talking about the thing that's applying the force upwards is the tension in the rope or the cable. Okay, so simplifying this, we've got a mass of 200 kilograms. We've got force upwards by the cable, which we'll call T for tension. And we've got, obviously, its weight downwards. Mass times gravitational field strength. So 200 times 9.8, which is 1,960 newtons. Okay, so what else are we told in the question? Something really important. Constant speed. So what do we know about forces, constant speeds? Balanced, yeah. So constant speed means the forces are balanced. So T, the tension, must be the same as the weight downwards. If it doesn't talk about air resistance, we're assuming that it's negligible. It will be negligible in this situation. Okay. So the important thing to notice is the upwards force in this case is your tension, the rope. Example 6b, the block is then lowered by the crane. Calculate the tension of the cable if the block accelerates downwards at 0.2 meters per second squared. So again, let's draw a diagram. So it's 200 kilograms. We've got the tension upwards. We've got the weight, which we now know is 1,960 newtons. And we've got an acceleration downwards, 0.2 meters per second squared. Okay, so if we're going downwards, we probably want to take the downwards arrows to be positive and the upwards arrows to be negative. So what we've got F equals ma, our unbalanced force. So our unbalanced force in this case, well, if it's going downwards, the downwards force will be bigger. So it's going to be 1,960. Take away the tension. (200 times 0.2). So 1,960 take away T is going to be 40. So the tension is going to be 1,960 take away 40. So 1,920 newtons. Which makes sense. If it's going down the way, the downwards force will be bigger than the upwards force. Okay, so same kind of thing than if you had a thrust with a rocket and you're ignoring air resistance, that kind of thing. But instead of a thrust, we've got this tension because we've got a cable or we've got a string or we've got something that it's attached to that's pulling it up and down. Okay, so that's tension. But you use it in the same way as you would thrust or driving force or anything like that. Example 7 introduces a little bit more complication because we've got two bodies tied together. Okay, but it's actually it's the same. If you do the same thing over and over again to answer these ones, so once you've done a few, you find out it's actually not too bad. Okay, so a ski tow pulls two skiers who are connected by a thin nylon rope, so they're connected, they're attached to each other, so there's going to be tension involved, along a frictionless surface. The tow uses a force of 70 newtons, and the skiers have masses of 60 and 80 kilograms. So we've got a diagram there. A, what is the acceleration of the system? So when it asks the acceleration of the system, that means you can treat it all like one big mass. So you treat those two skiers like they're just one mass. Okay. So acceleration of the system. So we can look at it like this. So we're basically 80, I'm not even going to try and draw people, 80 plus 60, one big mass, being pulled by 70 Newton ski tow. So it's frictionless, so we don't have any backwards force. So it's just as easy as going, and balance force is mass times acceleration. So mass is 140, the force 70 minus 0, so 70 times by acceleration. So the acceleration is going to be 0.5 meters per second squared. Okay. So if there's this two things tied together, two bodies, two blocks, two people, then the first thing to do is find the acceleration of the entire system. So just lump them together as one big mass and find the acceleration of the entire system. Because if we do that, the entire systems, they're both traveling at the same acceleration because they're tied together. So the system is going at the same acceleration if you took 60 on its own or 80 on its own. They're all going at the same acceleration. B, calculate the tension in the rope. Okay, so the tension in the rope, you can see there's a nice an arrow there. So that's what we want to find, that tension going in that direction. So what we want to do now is we're going to split them up, and we're going to look at the 80 kilogram person. Okay, so look at the 80 kilogram skier. So what have we got? We've got 80 kilograms with that tension forward. Because the 70 newtons is applied to the whole system, so we can't use that now. And we know that the 80 kilogram is traveling at 0.5 meters per second squared, because they're both traveling at that acceleration. There's no difference in acceleration. So to find that tension, unbalanced force is mass times acceleration. So T equals 80 times 0.5, so 40 newtons. So these often come up, these kind of questions. So the trick is you find the acceleration of the entire system, then you use that acceleration to find the force on one of the masses. So they do like to ask those kind of things. You could use 60 kg, but this force would be, you'd also have the force pointing in the opposite direction. So for the 60 kg one, you would have the tension pointing in this direction. So you have 0 minus 70. So if you had a 60 kg, you would end up with leave it with me a second because I'm trying to think, because you could use it, but you'd have to then incorporate 70 newtons as well. So leave it with me a second and I'll come back and go through that one again because I have to think about that one. Good question. Let me go through the last two examples, then I'll come back and have a go. Right. Last page before I get you guys to do some questions and I go and think about that one. When an object floats in a liquid or gas, both are fluids, it experiences an upwards force called upthrust. So instead of your engine force, or instead of a tension, you now have an upwards force called the upthrust. So for example, a weather balloon of mass 50 kilograms is tied to the ground by a rope. Okay, so there's another rope involved, so there's going to be tension involved again. The upthrust on the balloon is 780 newtons. Calculate the tension in the rope. So the first thing to do is draw a diagram. So we've got a diagram there drawn for us. So we've got an upwards force and upthrust. We've got the weight downwards, and we've also got tension downwards on the rope. So if it is tied to the ground, it is going to be stationary, or as stationary as you can get. So stationary balance forces. Okay, so the upthrust will be equal to the weight and the tension down the way. So you can work out that because you've got, we want to find the tension, we've got an upthrust of 780, and we can work out the weight, which is the mass times gravitational field strength. So it's going to be 780, take away the weight, which is 290 newtons. Part B, the rope tying the weather balloon to the ground is cut, so that tension no longer exists. The upthrust on the balloon remains the same. Calculate the upwards acceleration of the weather balloon. So in this case, we've got the upthrust, which remains the same, so 780 newtons. We've got the weight, which is mg, which we worked out to be, well, the question worked out to be 490 newtons. And we want the upwards acceleration. Yeah. So we do, for this one, F equals ma. There's a lot of F equals ma in this booklet. So this case, we've got upthrust, take away the weight, is the mass times acceleration. So 780, take away 490 is 50 times by acceleration. So the acceleration will be 290 divided by 50, which is 5.8 meters per second. Okay, so although it looks like there's a lot of new things been thrown at you there, all it is F equals ma over and over again. Okay. The only different thing would be that tension in between them. Okay. So I'm going to work on that question now. You can do your new question booklet up to question 16. Now, it's not a very big question booklet.